18, 17. Yeah, this would have been the year before you. So, have any of you discussed in earth science, or do you remember discussing anywhere spaghettification? Have you heard of that? So it's mostly something that people talk about with relation to black holes. The idea is you fall in the black hole like this woman in the picture here, and you get stretched out like a spaghetti noodle. Does that ring any bells? Oh, so somebody. Sorry, I'm checking to see what's on the chat. Oh, I thought somebody just typed something. Maybe it's telling me. Can you hear me okay? Okay. There was some message that just flashed there. I don't know what it was. Is it about the stream? It seems to be going okay. Oh well. So, anyway, I'm just going to read this. The sun, the moon, and the earth are continually spaghettifying one another. On earth, we see the effects of spaghettification in the form of tides. What causes spaghettification? Well, if you look at the woman there, the gravitational pull of a black hole is really, really strong, but it's not so much the strength of it as the gradient at which the force of gravity changes. So as you get closer and closer to a black hole, its gravitational force on you increases, but its force on the parts of you that are closer to it, like in the picture, her feet are closer to the black hole than her head. The force on those feet is a lot stronger than the force on her head. Right now, as I sit in this chair, or you sit wherever you are, the force of gravity pulling your feet down toward the floor is not that different than the force of gravity pulling a similar mass in your head down toward the floor. It's about the same. But if you get close to a black hole, your feet get pulled way harder than your head does, which effectively stretches you apart. If you think of people trying to rip another person apart, somebody grabs the head, somebody grabs the foot, they pull. It's not like that really at all, because if I have somebody's head here in this hand and their feet in this hand and I pull, to make this analogy right, well, there are a couple of things wrong with that. One is the feet are being pulled this way really, really hard. The head is being pulled the same way but not so hard. So they're going to get stretched out. But it's not just the pull on the feet. There's also a pull on the ankles and a pull on the shins and a pull on the knees. So this woman's not going to get ripped into two pieces. She's going to really get thinned out like a spaghetti noodle. And I don't think she would really break apart at all. Just get skinnier and skinnier, which is why they call it spaghettification. So this kind of thing also happens with tides. The Earth is sort of being spaghettified by the moon, but not the sun, which is kind of odd. So here we've got Newton's law of gravitation, which is the connection to all this. And then there's the moon over here, and there are three forces labeled F1, F2, and F3. And you could calculate the force of gravity on some water on the near side of the Earth to the moon. And you could calculate the force of gravity on some water on the other side of the Earth compared to the moon. And you'll get different forces. And just like with somebody falling into a black hole, the difference between those forces causes the Earth to get stretched out a little bit. And the part of the Earth that's most vulnerable to being stretched is the water. So that is one of the best ways to explain why there's not only a high tide on the side of the Earth close to the moon, but also opposite the moon. It's just, even if there weren't any water on the Earth itself would be stretched out, pointing at the moon. So this hump of water on the back here is just because it's not being pulled as hard as over there. Now, I asked the other group this question, and it was kind of interesting. I'm only going to ask it one way. I won't ask it both ways, because that could be potentially humiliating. And the question is, how relating to how much gravitational force the sun and the moon are exerting on you right now. So, which one is exerting more gravitational force on you, on me, on the water on the earth? Is it the moon or is it the sun? So if we, for example, I've got a spreadsheet where I calculated the force of the moon pulling on 1,000 pounds of water on the close side of the earth, and then the force of the moon pulling on 1,000 pounds of water on the far side of the earth. And I also did this for the sun. Which one, how many people think the sun is pulling on us harder than the moon with more force? Raise your little fake hand if you think so. And I'm going to introduce you to Murray, and then I'm going to kick Murray out. This is Murray. Couple people, 3 people think that the sun's pulling on us harder than the moon. 4 people. I said, well, one hand went away. All right, Murray's going to go. So I won't ask other people to take the other stand. Go, Murray. Go. Be right back. I'll just go to my spreadsheet and show you this. It's kind of interesting. I mean, I could see the reasoning either way. So the left side of the spreadsheet, this is where I've got all my data, like the masses of all these objects. And this one, where it says the mass of an object on the Earth's surface, this so-called object is just this is 1,000 pounds of water. It actually comes out to not exactly 1,000 pounds of water. Sorry, not 1,000, 1,000,000 pounds of water. And here are some distances from the Earth to the moon, Earth to the sun, the Earth's radius, and then I've got distances from the near side of the Earth to the moon, and the far side of the Earth to the moon, and then the near side of the Earth to the sun, and the far side of the sun. Here are my calculations. So this is all, oh, and up at the top, I've got my all-important gravitational constant right there. So that's big G, which allows me to calculate all these things. So this is just to show you how much water we're talking about. So you have a blob of water, and I calculated that would be about 31 feet in diameter. So picture a sphere of water, 31 feet in diameter, sitting on, in this case, the close side of the Earth to the moon. The force of gravity is 3.5 pounds. So if you just imagine a blob of water 31 feet across, floating in space by itself, and being pulled toward the moon with a force of 3.5 pounds, which is not going to move that water fast, but it would move it if there were no friction or anything. And then on the far side of the Earth, this is the force, 3.28 pounds. And if I do that for the sun, 601.34 pounds. So the sun exerts about 200 times the force that the moon does on the water on the Earth. And then on the far side of the Earth, the sun pulls at 601.23. The important thing, though, is the difference. If I find the difference between the moon's pull on the near side and the far side, it's almost 1/4 pound. If you do the same for the sun, it's only 1/10 pound. So this is the spaghettifying force. It's the difference between the pull on the close side and the pull on the far side. That's the force that's kind of ripping the Earth apart and causing the water to get pulled to the different sides. So even though the moon is so much weaker than the Earth, because it's closer, the rate at which the gravitational force decreases or increases as you get closer or farther is greater than the sun. Sun's so far away that just the diameter of the Earth doesn't make much of a difference in its two forces, so it doesn't do much with regard to tides. It doesn't spaghettify the Earth much. So yes, if the moon had a stronger gravitational force exerted on the Earth than the sun did, then we would orbit the moon, not the sun. So this next One. Number three, even if there were no water on the earth, there would still be tides, just as there are tides on the moon. I don't know, or maybe I should say just as there have been tides on the moon. Does anybody know what I'm talking about? How could there be tides on the earth if there's no water? I'm going to draw for a second while you consider that. Here's the earth, here's the moon, and this is totally not to scale. If I really made this to scale, it'd be something like the earth is this big and then the moon is that big and that far away, but I want to fit them on here. So, no water on the earth, how could there be tides? Anybody know?
Could it be like the plates underneath the Earth?
Kind of. I mean, the earth itself, it can't move as much as the water. The water is easy to shift around on the surface, but if the near side of the earth is being pulled with a force of gravity that's that big, and the far side of the earth is being pulled with a force of gravity that's that big, what happens is that the earth gets sort of tugged into this egg shape slightly. Even it's enough to deform the actual rock and dirt and all that in the earth. Even if there were no water, we would still have a tidal hump on the opposite side from the moon and a tidal hump there, and everything would be stretched out like this, spaghettified. So what happens is, over the course of a day, as the earth rotates, let's just say this is the North Pole, maybe Vermont is right here, and the earth under our feet is actually stretched toward the moon a little bit. And then we shift over to here, and all that stuff that was stretched recedes back in toward the center again. And then we get over here and it gets stretched out again, and then it goes back in. And all that friction over time, guess what that does to the Earth's rotation? Speeds it up or slows it down?
Slows it down.
Slows it down, yeah. The Earth used to rotate really fast relative to how fast it rotates now. Days, if we use the same length for an hour, the rotation of the Earth at one point was 10 or 12 hours instead of 24 hours. But over time, this loss of energy due to the friction of the Earth constantly spreading out and squishing back together in different places has slowed it down. And the same thing with the moon. The moon, I don't know if you could say it has tides today. There's sort of a perpetual high tide on the near side and a high tide on the far side, and that's just where the land is a little bit higher. But the moon has stopped. It used to rotate relative to the Earth, but now if I draw an X here, this X is always pointed at the Earth. A long time ago, that would have been going back on the back side and coming back toward us again back here, but friction has already slowed the moon to the point where it's locked in with us, where we always see the same side of the moon. And it's because of that friction from tides on the moon. See if there's anything else here. I guess that's it. Let's see what this link is. I haven't looked at my links in a long time. This may not even work, but is the Earth's 24-hour rotational period speeding up or slowing down? It's like some astronomy website. Oh no. That doesn't look like it's going to get me right to the answer really fast. I'm going back, fleeing. So does anybody have any, this is nothing I'm going to test you over, but does anybody have any questions or comments about that? Just a good application of Newton's law of gravitation. All right, review the homework. Nobody really had any questions about the homework in the other class, but that doesn't mean you can't ask questions about it. You're supposed to do number 14 and number 15 on here. Does anybody want me to walk through any parts of this? No? Okay. So let me tell you about somebody does. Riam.
Just if you can review number 15.
15, sure. Let me move my camera a little bit closer. So both of these are applications of Kepler's third law, which is this. And in number 15, we've got Europa which is a satellite of Jupiter. It's one of the moons of Jupiter, and it orbits every 85.2 hours. So that's an orbiting body, and this is the period of its orbit, and at an average radius of that. So we're given the orbital radius, and so this would be the period. I've called Europa letter A, so this is the period of Europa, and this would be the orbital radius of Europa. Ganymede is another moon that orbits Jupiter, and it orbits every 172 hours. So that would be the period of Ganymede, which I've decided to designate with a B. And so we're looking for Ganymede's orbital radius, which would be RB. So here's the formula that gives us the relationship between periods and orbital radii of two objects orbiting the same thing, which is they're both orbiting Jupiter here. And I just decided Europa was going to be A in my equation, so here I've plugged in Europa's period squared, and that's over the period of Ganymede, which is 172 squared, and that equals the orbital radius of Europa, which is this, to the third, over RB to the third. And then you can, I guess I cross multiply. I don't know. For some reason I don't like the term cross multiply, but you can cross multiply to solve this, and once you cross multiply, then you'll end up having to divide both sides by that to get the answer. And then take the square of the cube root. So, but once you have this, it's just computations. And if anybody wants me to go over this, stay on after the meet, and I'll do that. Any other general questions about either of those? Okay, let me say a couple of things about the homework assignment. First, I lengthened it a bit because it seemed like what I had assigned before was just a little short and kind of I don't know, felt like wasting time. So it's on pages 9 through 12, and now it may be a little bit long. So if you feel like you're being overworked and overburdened and abused, just stop, do whatever of this you think is helpful to you. So this was the test a couple years ago, not a couple, 2018, I think, would have been when I gave this. And it's okay. The reason it's not the test anymore is because it's not as good as the test. The test is, every question is fairer and better on the new test. Couple of things. This says astronomic. I don't know if that's my fault or if that's somebody, Mr. Pennington, that did that, but that should be astronomical unit. And when you get to number 9, this one is really not very well done. I would like to point out that basically what you're supposed to do is look at these segments. For example, C to D, this time period between when a planet's going from here to there, and you find another segment that represents an equal amount of time. So, for example, A to B. If you think it takes just as long for something to go from, actually A to B is not a choice. Let me look at some other choices. E to F. If you think it's going to take just as long to go from C to D as it is from E to F, then you circle both of those. Like you would say, C to D, E to F. Those are the two. Now, there are a couple of them that are conspicuously lacking. You can't choose A to B, that's not a choice. And neither is B to C, that's not a choice either. So keep in mind your only choices are C to D, D to E, E to F, F to G, and G to A. And it turns out that there are, I think, a couple of acceptable ways to answer this. This is not a great question, but do the best on it. Just notice if you think, well, it could be this, but it could be this. I think you're probably right. So the important thing is to know how to do it, and we'll talk about that later. Just wanted to warn you on that. Yeah, I think if you did it all, some of you will be able to just use the rest of the time remaining, rest of our little 45 minutes here, plus, another half hour, and you might get done with all this. Some of you, that's not enough time. So just do whatever you want, and you can always work on this later. I plan on giving you another practice test, which will be one of the actual tests from last year. But essentially, we're done with everything. We're just kind of practicing, polishing things up, putting it all together. I'm trying to ask you questions that'll trip you up and make you get it wrong before the test, so that won't happen on the test. So that's it. Does anybody have any? Well, let me stop the stream.